Okay, welcome to this session. We want to jump on to question 6. Hopefully you found our videos very interesting and hopefully you've been able to understand and comprehend the questions that we've done starting from question 1, question 2, question 3 up to question 6 that we're able to do today. So I invite you on this platform. Let's see how best we can identify different kind of products on this given chemical reaction. So we'll look at question 6 today, and I want to make it very clear here. I'll jump on from one step to the other so that we're able to fully comprehend and understand how we're supposed to go about the chemical reaction. So the first thing that we're supposed to identify here is this. What have we been given? And I'm also going to reduce on the emphasis of the word here, as I'll try to replace that word with a different one. Uh, so we are having the the hydrogen ion here. Okay, so we're having the hydrogen ion there, and then we're trying to see what we can do. We're trying to see what major products can we get after reacting it in the presence of the hydrogen ion. So it's quite very easy. I want you to know that this hydrogen ion that is here, it might have come from the acid, it might have come from the water, it might have come from um, the acid itself. So it had initially it came from somewhere, and that's the reason why it's there. And there's a reason why it's there. Okay, so I'll provide the reaction mechanism to show how everything is supposed to be done. So I want you to note that the ring that has been given here has got two different groups. We've got two R groups that are here, and we're also having the oxygen that is right there with the two lone pairs of electrons. So what will happen is that these two lone pairs of electrons are negative and this is positive. So we're going to expect an attack from that point to come and pick up the what? The hydrogen ion that is right there. So after that attack, we're going to have this product. Somebody was telling me that you shouldn't just be putting up these reaction mechanisms, but you must explain the reason why all that is happening. So I'm trying to put out the point to say this oxygen here is negative and it's very reactive because of the lone pairs of electrons that it's carrying. And then you have the hydrogen ion that here is that right there that is positive. So what will happen is that the negative part of the oxygen is going to attack the positive part of the hydrogen, and then you're going to have that attachment. So when this oxygen combines with the hydrogen, you're going to expect to have what? An hydroxide or H. Then the rest of the structure will proceed on like that. There we go. So you have the R group there, you have the other group right there. And then don't forget the double bonds that are within the ring. What's the next step that we're supposed to do? So now I want you to know that since we formed the alcohol as part of the structure that we are having, an alcohol is a very good uh, donating group. It donates electrons. Let me put that point up. So this alcohol that you are seeing there, the alcohol, it is a very good donating group. Donating what? It donates electrons. The electrons. Good. So what will happen is that this, oh my goodness, sorry for that. So what will happen there is that the the hydrogen that is there, the hydroxide that is there, because it is the hydroxide, it is going to donate a pair of electrons down the ring or down the structure. So you're going to have these number of electrons coming right there, and you're going to have this double bond within the ring shifting to that point. And what we're calling that, entirely what we're doing here is resonance structure. So because we're having the alcohol as part of the ring and it is very good at donating electrons, so it's very possible for us to have a resonance structure in this compound. So all that I'm trying to do here is resonance. So the other structure that we can have apart from the one that were formed here is this other structure. We're going to have something of this kind. So there we go. There we go. This bond here has been broken because the electrons have been brought down there in the structure. So we're having OH, and this is a single bond connecting down there, connecting down there, and there we go. We have our arrow groups and the arrow group there. So after having that, remember that there's the double bond has shifted from that point. We are now having the double bond here, and the other double bond is right there. So because there's a shift to the double bond from that position to that position, we are going to have a positive ion right there. So there's formation of the positive ion because we just moved the double bond from that position to that position there after the hydroxide donated the electrons from that point to that point by breaking down the double bond that was there. So we now have the formation of the positive ion. And you want to say this can't just remain like that. We have to get rid of it. And getting rid of that thing, that's positive ion there, entails that we are having a tertiary carbon here because it is connected to three different groups. You have the arrow group there, you have the arrow group there, it's also connected to that part, it is also connected to that part. So you're going to have hydronium shift. You're going to have what we're calling hydronium shift to stabilize the structure. Hydronium shift. So this hydronium shift, let me use a different color for it to see what I'm doing. So this hydronium shift, how it's going to happen is this. You're going to have this coming there, and then you're going to have this going right there. And then your final structure now proceeds as this. You have that. So we have one arrow group there, and then because hydronium shift, the positive ion has moved from that position, it has come right there. And then the other arrow group has moved from that position, it is now right there because of the hydronium shift. Remember, don't forget the double bond that we're having, the one at that position and the one at that position, which is also connecting directly to hydroxide, the single bond, because that was already broken down. We know how that step came about. What next are we supposed to do here? We still can't leave the positive ion in that position. We still have to remove it out. So the other step that is going to proceed right there is that we are supposed to identify a few things. This arrow group here has got the hydrogens. It has one hydrogen at that position because this carbon has got this attachment, one here, two there, three there, and then the hydrogen that is attached there. So this is what we're talking about. So coming down there, we have this structure. We have that, we have that, we have that. That's the OH. We have that, then we have that, we have that, we have that, and then we have the arrow group. So the point I'm trying to put across here is we have the arrow group, and this arrow group has got hydrogen at that position. So to stabilize all that, what will happen there is that I told you to say the hydrogen here is coming from a compound. It was an acid, and maybe that acid was the sulfuric acid. So at this point, this is what I'm saying. We have the hydrogen, and we're also having the arrow group. And in the compound, I was trying to emphasize to say this hydrogen that was given here as our reagent, it came from an acid. That acid could have been a sulfuric acid, that acid could have been hydrochloric acid, and so on and so forth. So but I'm going to use sulfuric acid so that I can get rid of this hydrogen at that position, SO4, because we have the oxygen there that is going to get rid of this proton there, and then these number of electrons, because remember we still have a positive charge right there, and these number of electrons are going to come and attach at that point, because the proton of the hydrogen has been taken by the oxygen from the acid, and then the number of electrons that are going to remain at that point are going to come and attach at a positive to stabilize that. And don't forget, within the ring were the double bonds at that position and at that position. So therefore you move on, and then our final structure is therefore going to be this. We have that, the single bond, you have that, down there, down there, down there. Don't forget the arrow group. So I was saying that these number of electrons are moving from that position, attaching at the point where we have the positive ion, so we're going to form a double bond at that position within the ring. And then the other double bond was that position there. The other double bond was at this position, and then we still have our arrow group at that position. And this is your final structure. So this is how you're supposed to work it out. This becomes your answer. So remember, the question is saying identify the products in these chemical reactions. So I was just trying to see how I can work around the entire chemical reactions by using the things that I already have at my disposal. I already have the structure. I can play around with using the resonance structures and see how I can move along. And so this is our final product. So that is how you get it. So this is how you're supposed to work out question 6a. So now let's move on to question 6b. Okay, I'll keep it easy and straightforward. I hope you got the logic from there. So B, the structure is given like this. So we add that, then we also add that structure there, and then in this structure here, which is a ketone, this is a ketone. It was reacting in the presence of what? This ketone was reacting in the presence of, there's a ketone group there, okay, OH. It was reacting in the presence of this structure. This structure is called MCPBA. The structure of MCPBA is this. So I'll still point out to say this structure is MCPBA. For what do we use this structure? It's used to make an epoxide from, like when you've been given a reactant to a structure, then you've been given MCPBA reacting with MCPBA, and alkene reacting with MCPBA. You're going to form an epoxide from that structure. So now the general structure of this MCPBA is like this. We have a chlorine there, then we have a ring. It has a ring with the double bonds inside, which is connected to this point, and then the OH. So now you can see that this structure here that we're having right there is this structure right there, and the other group was not just put plus the chlorine. So this structure is MCPBA. It is therefore there to for the formation of an epoxide. That's what MCPBA does. And the other words that you can use to give a full description about MCPBA is the pala acids, as others describe it. I don't know how you are supposed to describe it, but that's the MCPBA abbreviated in that manner. So now we're trying to find out what's the major product after reacting the ketone, because I'm telling you to say this is a ketone. So we want to find out the product after reacting the ketone in the presence of MPBA. What is going to be our final product? So let me tell you the final product, and I show you the reaction mechanism. I want you to note to say in this ketone right there, we have a methyl group. This is a methyl group right there. And then the other group there is isopropyl group. And if I were to ask you a question, which one is more substituted between the methyl group and the isopropyl group, you would respond to say the isopropyl group is more substituted as compared to the methyl group. So this one has got higher steric hindrance as opposed to the methyl group because it has got less number of carbons and the chain is very small as opposed to the isopropyl group. So now one thing that you must understand is that when you have been given MCPBA, you're trying to form an epoxide and you're just going to cut a structure in between to add an oxygen. That is how it works out. Now the question is that which part are you going to add the oxygen? Is it on the part of the methyl group or on the part of the isopropyl group? So I'm trying to point out the fact that that oxygen is only added at the most substituted part, which is this point here. So the final structure we're going to have after this is this other structure. This is going to be our product. The ketone will still remain, and then in between here we're going to add an oxygen connecting the isopropyl group. I just put the oxygen on the part where it is more substituted. So that is the final product we're supposed to get after undergoing the reaction mechanism. So now for us to understand how we're supposed to get to that product, I want to provide a synthetic scheme or a reaction mechanism to show how we're supposed to get at that point. So now let's proceed. Okay, so our structure was this. This is a ketone, our reactant that we were given. React in the presence of MCPBA, this structure right there. And then we are having the hydroxide. Apologies for that. And we are having the hydroxide. Okay, so now what will happen here is that we are going to identify what we are having because our structure here can be written as this. There's a double bond there, then we have the oxygen there, then it is bonded to another oxygen, and this oxygen is bonded to what? The hydrogen. So we know that this has got the lone pairs of electrons. This also has got two lone pairs of electrons. And this compound is what we are calling as MCPBA. So what will happen here initially is that we are going to have an attack. And this attack is going to move from this oxygen here, attacking the other carbon here because this carbon is positively charged. And this carbon here, this oxygen here is negatively charged. So this is more negative as opposed to the carbon that is there. So we're going to have an attack from this position, attacking at that position. And when you attack at that position, we're going to have the double bond connecting to the oxygen, breaking, and the number of electrons will join right there. So what are we going to have after that? The structure we're going to have is this. I'll still maintain with the color. We still have that bond. And then this has now become a single bond. And then the number of electrons here, the lone pairs of electrons are going to increase. And this is going to become negative or more reactive. And then remember we have the isopropyl right there. So it's going to connect down there. I still have that compound. And then we have an attachment of this other compound right there. So this compound is directly attached to this oxygen. And this oxygen has what? This oxygen here has got the hydrogen that is right there. So I'm going to indicate that down right there. And then it is also connected to what? To the oxygen, which is right there. And this oxygen is connected to a ketone group. Up like that. Let me draw it properly so that you're able to see. It is connected to a group up there. And then down there it connects. So we're having that structure right there. So now one thing that we must understand here is that the oxygen that is in this compound is very reactive because of the presence of the negative ion that is present. So it is going to look for a proton to attack, and that attacking of the proton is what we're calling a proton transfer or an intramolecular reaction because it is happening within the structure. And the proton that is available here is this one there. So we're going to have an attack from this position here, coming to attack, coming to pick up the what? The proton. And this number of electrons will come there. So the other structure we're going to have after this is this. I hope it's very visible from your position or from your view. So we're going to have this structure. We're still going to maintain there. Then up there, we still have OH. Down there, we still have that position. We still have that isopropyl group. And then connecting to the oxygen with two lone pairs of electrons. And the other two lone pairs of electrons, the two lone pairs of electrons connecting to the oxygen. And then this other oxygen is connected to this other group. That is what we have there. So we're having now, what has changed about the structure that we had there is the presence of the hydroxide that is now attached. What's the next step? So I was trying to mention the fact that we have a methyl group right there. This is a methyl group, right? And this other group is an isopropyl group. And I was saying the isopropyl group is more substituted as opposed to the methyl group. So this is the one that is supposed to attach to the oxygen that is right there, which is having the two lone pairs of electrons. So we're going to have an attack from this position to that position. But before that position is done, I also told you in the previous question to say the hydroxide here is a very good donating group because it loves donating electrons. So it will donate the number of electrons, the two lone pairs of electrons, right there to form a double bond. And after donating, what will happen next is that this group will be kicked out. And then this other group here, which is the most substituted batch, is going to attack at that point. And then now this is going to leave. That structure goes. And then our final product now is going to be this is now going to become a double bond. We have our methyl group. That's the first thing that we must notice there. Then we also have a double bond now in between there to OH. Then down here we're having, so we're splitting this isopropyl group because it is more substituted and it's now holding on to the oxygen. So we're going to have this oxygen here coming in between, then the isopropyl group goes like that. Then plus what else? So this oxygen has already come there. This structure is now what is leaving. So the two lone pairs of electrons are now attaching there. So I have two pairs, the two lone pairs of electrons that are moved from this point are joining that structure there. So I have the oxygen right there, and then there, this is more negative, so it's more reactive. And then we have our compound right there. So we can't leave this structure like this because it is more reactive. And I told you to say, when you see an oxygen in such kind of a state, it is very reactive and it will look for a proton to get. And the proton it's going to get is a proton right there. There's a proton there. So it will just get a proton from there. And then, because this proton is attached to the oxygen, it will leave its number of electrons on the oxygen. So in other words, I can write it like this. Because you know that this is attached to the oxygen and this is very reactive, so we're going to have a reaction here where this is getting that. Let me use a different color so that you're able to see what I'm doing. So this is going to attack that, and when it attacks, these numbers of electrons will come there, and our final structure is going to be what? Our final structure now goes to be this. So this oxygen here remains alone. Then the methyl group now follows on. The isopropyl group follows on. Then plus what else? Then we have hydroxide here, HO. And then we have that. And then we have that. And this becomes our final answer. So you can tell that this is what we had initially when we were trying to make those predictions in the absence of providing you a reaction mechanism. So we still have the first structure, the correct structure that we had initially, and then the second structure also. Remember the question was saying predict the major products. It did not say predict the major product. So we're not only restricted to one product, we can even have more than two products in that chemical reaction, proceeding on to whatever has been given there. So this is how you form the epoxide, and that is how it entirely works out. One thing that I want you to understand from here is the structure of the MCPBA and the role that it plays when it reacts with the ketone, the role that it plays when it's reacting with the alkenes. So this is entirely how you're supposed to go about the reaction mechanism. I know it's a bit complex and it's very difficult to comprehend certain things, but I would suggest that we go through a number of videos and see how we can understand and comprehend and have better insight over this such kind of questions. So if you want, you can still pause the video and see how I was doing certain things. So this is our B. Let's proceed on to C. So question C was what structure? So question C was a question like this. Let me use a different color. We've used zero too much. So let me use white. C is this structure. We have a ketone, and then the other structure that we're given was an enolate. And you know that when you're having a ketone reacting with an enolate in the presence of such kind of reagents, there's an ethyl there, an oxygen, and Na. You know that to say this is an auto condensation reaction. So I first of all want you to note what we have in this structure. We're having the ketone, this compound, we're having the ketone, we're also having an enolate. And we want to ask ourselves, what is more reactive between the ketone and the enolate? And we know to say the enolate is more reactive as opposed to the ketone. So what is the first structure that is going to initiate the chemical reaction here? So we are having the ethyl sodium, the ethyl oxide, that is it present in this compound. So you can also write it in this way: 1 2, then we're having that. So the sodium is just reacting as a spectator ion. It plays no role here. It's just reacting as a spectator ion. It doesn't play any role in this state. So this is just a spectator ion holding on to stabilize the structure here. So we're having this. So the first thing that is going to happen here is that this enolate here, because it is more reactive, it is going to be attacked by this structure, our reagent. We know to say this one here has got, there's a hydrogen there, because this is what this is there's a carbon here attaching to the first structure: 1 2 3 and 4 bonds. So we are going to have, this is negatively charged, and this is going to attack this oxygen, is going to attack the proton there, or the hydrogen, and the lone pairs of electrons are going to remain right there. So after that, we're going to have this structure. I'll maintain my ketone. It has not reacted. I said what is more reactive here is the enolate, and it is the first. It was the first one to react with the reagent. So we have there, then we have there, we have there, we have that, and then we have the two lone pairs of electrons. So having these two lone pairs of electrons makes this enolate even more reactive, and it even makes this carbon here more negative. So we're going to have an attack from that carbon now attacking the ketone. So from that point, this is going to attack that, and this is going to join. And once it joins, this is the product that we are going to have. So let's look at the structure we're having when that joins. We'll be having this structure. We'll be having this structure. Remember, I'm still going to, because there's an attack from this proton, this carbon is more negative as opposed to that carbon. So this is partially positive and this is partially negative. So this attack is going to move from the part that is partially negative to the part that is partially positive. And this double bond here is going to break, taking the number of electrons right there. So we're going to have that. And this is now a single bond with these number of electrons. This makes it more reactive because you can leave the oxygen in that state. We still have that group right there. I'm still going to put it there. That's a methyl group. And then there's a bond that is now connecting from that oxygen to the other oxygen. It is going to go like that. Let me change the color so that you see. There's a bond there. The bond that is connecting from that point to that point. There's a bond. And then after that bond, there's a double bond. Okay? After that point, there is a double bond connecting like that. Then after that double bond, there's another bond that is now attached to that other structure there. So there, 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 and then there's a methyl group there. So we're having that structure there. And what is going to happen next is that You can't leave the entire structure in this way because you know the oxygen can't remain like that because it is reactive. So what will happen is that remember that when we had this compound, it had taken the hydrogen, and what we have in the solution is this OH. So since this is going to look for a proton, it is going to come and attack which proton? There's a proton there, and the number of electrons are going to remain there. So what is going to be our product? We're going to have this. We're going to have that there. Sorry, a minute. We're going to have that. That's what I have then, and then it is now connecting to the OH because you know this has now taken that, and then down there we have a methyl group which is connected to that point. Then we have a double bond right there. Then down there we have a ketone. So this becomes our product, and that is the answer. And this is how you're supposed to break out C. So it's quite easy. Just follow through the reaction mechanism and see how you can break out this reaction. So one thing I'll point out is this. The sodium is acting as a spectator ion to stabilize the reagent. And when it has been stabilized, it is very easy for it to react with the most reactive between the ketone and the enolate. And I mentioned to say the enolate is more reactive as opposed to the ketone. So when that reaction takes place, we are now going to have the ketone being more negative as opposed to we're going to have the enolate being more negative as opposed to the ketone. Then the enolate is going to attack with the ketone, attach and forming our final structure as this compound right there. So that's how it works out. Let's look at question D. That's the last question for question 6. That's the last part for question 6. D. So D is quite easy. The structure is quite easy. Let's see how we can bring it down as well. Okay. I'm trying to look for the question. Okay, I've seen it. It's right there. Okay, here we go. So we had that. Then we had that structure. Plus we're given, okay, back to my favorite reaction. We had the phenyl group there. Then this phenyl group was a positive, and then it is attached to CH2. They double bonded to another CH, double bonded to another CH2. Then we have the chlorine there, and then this was in the presence of what? Of the ethyl. Okay, then we have the sodium there, which is a spectator ion there to balance the reagent or to stabilize the reagent. So what's the first thing that is going to happen here? I want to show you the structure that we are having initially. This structure here, I want to write it down in a proper manner so we're able to see what is there. So this structure is written like this. We are having the phosphorus, which is connected to 3 phenyl groups. The phosphorus is right there. It is positive, connected to 3 phenyl groups. This phenyl group is there, which is pH. The other phenyl group is there, which is pH. And the other phenyl group there, which is pH, which is now single bonded to a carbon. And then that carbon is connected to one hydrogen. In fact, it's connected to 2 hydrogens. So if there's a hydrogen there, another hydrogen here, then there's a double bond in between. And how many number of bonds is carbon does carbon have here? 1, 2, 3, 4, 5. So it means that there was a mistake here. This was only supposed to be one hydrogen. This was only supposed to be one hydrogen because of the double bond that we're having. Or it's either we're the single bond right there to stabilize, because you know to say carbon can only be connected to the maximum number of 4. It can only bond to 4 other groups. So this is 1, 2, 3, 4. Great. which is now connected to a carbon. Wow, we're changing colors. Let me just stick to yellow. Connected to carbon, and then that carbon is bonded to the hydrogen, which is now bonded to the CH2, Cl. That's what we're having right there. That's what we're having right there. So what can we do? So there's a reason why we've been given this reagent in the reaction. It is playing a role. Now the question is that what role is it playing? The role that the role that that structure, that reagent is playing is this. It is going to look for a proton or a hydrogen to attack, and when it attacks that hydrogen, it is going to leave that carbon with lone pairs of electrons. That is going to make it more negative. This is what I mean. Being given the ethyl, then there's oxygen there. 1, 2, 3, 4, 5, 6, and this is negative. So it is looking for something to attack, and it is going to attack, therefore, the proton or the hydrogen that is there, and then this is going to give up its a number of electrons attaching right there. So what are we going to have? We're going to have something of this kind. We're going to have something of this kind. Let me put it right there so you're able to see. Okay, that doesn't look good. Let's do this. We're going to have something of this kind. We have the phosphorus, which is positive there, attached to 3 hara groups. I'll just replace the phenyl groups with the ara groups because there are 3, it's still fine. The ara groups there, and then it is connected to a carbon, and this carbon here, remember, the lone pairs of electrons are 2, the ones that came from the hydrogen, because the hydrogen has been taken by this compound right there, which is now connected or double bonded to the other carbon, and then this carbon is straight up there, and then it is connected to a CH2 Cl. That's what we're having right there. What's the next thing we're supposed to do? So now that we know that this carbon here is very negative, and this phosphorus here is positive, so we're going to have an attack. What are we having? We've been given a ketone. This is a ketone. So this ketone here is now has the ability to attack the carbon here because it is more negative. In fact, what will happen here is that this carbon here, because it is more negative, has the ability to attack the ketone, which is the major reactant in this reaction. So we're going to have an attack from the carbon coming to attack on the what? On the ketone. So now this structure here is very capable now to react with the ketone and find out the final product. So what we are doing here is trying to come up with the resonance structure and trying to see the role that the reagent that has been given, the role that the reagent that has been given is playing in this reaction. So let's proceed and see what we're going to get. So like that, and then down there we have that, and then the other force, we know that this is reacting with this, is now reacting with the 3 phenyl groups. I'll say 3. Then the phosphorus is positive now, which is now bonded to the carbon, and this carbon is very negative because of the 2 lone pairs of electrons, and then now it is bonded to the rest of the structure, 1 carbon there, and then the rest of the structure CH2 and Cl. So Cl. So what will happen here is that we're going to have an attack from this position going to that position. Why am I attacking there? This is very partially negative, and this is partially positive. So an attack can only happen from the negative part going to the positive part. And what are we going to have when we do that? We're going to have this structure. I want you to see it. We're going to have something of this kind. So after attacking at this position, this is going to lose. It's going to break down as well. and then the number of electrons here on the double bond are going to break and then will be taken to the oxygen. So there we go. Okay, 1 2 3 4, and this has become more negative. So now we have our methyl group right there. Now it is a bond straight to a carbon. Then this carbon is connected to a phenyl group, a phosphorus group, which is positive, and this phosphorus is connected to three phenyl groups. That's what we're having right there. And then this other carbon right there, which is now connected to the ketone which has just been broken down, is connected to a different group. In fact, double bonded to a group which is C, which is having one hydrogen right there, and also CH2Cl. That's what we're having right there. What's the next thing we're going to do? The next thing we do here is if we're going to identify, you know that this oxygen right there is more negative, and it is going to find the proton to attack. But it's not going to attack the proton because we have phosphorus here, which is more positive as opposed to the proton. So we're going to have an attack from the oxygen attacking the phosphorus right there, and it will join. What are we going to have after that? We're going to have this structure. I'm going to write it down there. So after that, I'm still going to maintain my structure. It is that point, and then that point. This oxygen here is now connected to the phosphorus, and this phosphorus is now connected to three phenyl groups. And then down the phenyl group, we have a carbon, which is double bonded to a different carbon, and this carbon is holding on to one hydrogen, and then the rest of the structure comes through. Good. Then down there, we have our phenyl group, and then there's a bond straight to the carbon. So I'll also try to point out one thing here. That thing I'm trying to point out is this. I want you to understand the electronegativities of different kind of elements. The carbon possesses a type of electronegativity. It has a certain number. So let me just try to explain a few things before I proceed on. The electronegativity of the oxygen is 3.5. The electronegativity of the phosphorus is 2.1. The electronegativity of carbon is 2.5. And the electronegativity of the carbon right there is 2.5. Why am I putting up these numbers? What analogy am I trying to put about? This is what I'm trying to say. I'm trying to point out the point that the electronegativity of that element determines the number of electrons that that element is able to hold on to. So since the carbon here has got an electronegativity of 2.5 and the phosphorus here has got an electronegativity of 2.1, what will happen is that this phosphorus here will not have the ability to hold on to electrons. So therefore the bond is going to break and it's going to go to the part which is more electronegative, and that's the carbon with an electronegativity of 2.5. So this bond is going to break. And in the number of electrons are going to move from the phosphorus joining the part for the oxygen, for the carbon. And then right here, we have in the carbon with an electronegativity of 2.5 and the oxygen with an electronegativity of 3.5. What will happen here is that the carbon cannot hold on to the number of electrons, and what will happen next is that this bond right there is going to break, and these electrons will move from that position going to join the oxygen because it has a more or a greater electronegativity as opposed to the carbon that is right there. So what are we going to have after that? What will happen is that this bond right there is going to go together with the OPH3, and then this bond right there is going to form a double bond connecting the rest of the structure, and that becomes our final product. How easy is that? So let's proceed. So we're having that. So the bond is not there. Sorry, apologies for that. Let's come right there. Our final answer now comes to be this. We go there. I'll still maintain we have this structure there. So I'm saying 1 2, and then this bond is no longer there, and then this is now a double bond. A double bond to a carbon. This bond is no longer there. It is just bonded to the rest of the structure, which is a double bond to a CH2Cl. L. So that becomes your final structure. How easy is that? So guys, this is how you're supposed to work out question 6. I hope you got something from this question. Please feel free to get back to our inbox, come through and try to ask questions where you're not so clear, and let's try to see how we can help one another. I'm not the best in this, so we're just trying to assist one another and see how best we can proceed in this course. So this is Arine Chemistry and Functional Group. I just looked at question 6. I'm proceeding on to question 7 and question 8 as the last question in the tutorial sheet. So get back for more videos, and please don't forget to subscribe. Thank you.